Now that we've learned bagging, is there a way that we can improve upon it? The answer is definitely yes. What we can do is think about how to pay attention to which examples from the previous learner that we've built are well classified and which we got wrong. And because learners always learn from the cases that they get wrong, what we want to do is increase the weight of examples that we get wrong and decrease the examples of the weights that we get right. When we create a new data set, we're going to try to mirror this by weighting certain examples in this way. This leads us to the idea of boosting, not to be confused with bootstrap, which is what we introduced in the last section. Boosting is an ensemble meta-algorithm that creates strong learners from weak learners. And what we mean by weak learners are ones that work slightly better than random, but most importantly, that have a very low bias, meaning that they are simple and generalize well. This means through the idea of using weak learners, we can address bias, and by the use of bagging, we can address variance. Let's see how this works. We're going to go through the idea of adaptive boosting, or AdaBoost, which works on binary classification, although it's been extended for multi-class classification as well. We're going to say that we're going to create a weighted ensemble of classifiers where each of the classifiers, h of t, all the way to capital T, is going to be weighted by a parameter alpha, which indicates its strength, and the individual models that are making their prediction on a particular input, xj. Each of these classifiers, as we said, has a tuning parameter that's associated with it called alpha. And basically the idea for alpha is to weight the classifier in some way to indicate how well it does on the entire training set. If it makes a lot of mistakes, then we want to lower its weight, and if it does very well, we want to raise its weight. Let's examine the case where the misclassification rate is fairly low, for example 0.1. In this case, let's investigate what we would have in our parentheses. We'd have 1 minus 0.1 over 0.1, or 9. So that's a fairly large number. Let's now investigate the case where the misclassification rate is 50%, meaning it doesn't help at all. In this case, we have 1 minus 0.5 over 0.5, and that's going to equal 1. It's a much lower rate, and after we've taken the logarithm, it will be equal to 0 weight. What do you think will happen when the misclassification rate is very high, like 0.9? In fact, that's very good in the case of having a binary classifier because we can just flip it around. We can use its misclassification and say to vote the other way. If it decides to vote negative, we would vote positive. So for example, when we have a classifier that works worse than 50%, we'll have a case over here. And we can just flip the decision the other way around and use the inverse of its decision. We can show, outside of the scope of what we're going to learn in this course, that all of these alpha coefficients will be the minimizer of an exponential error function, which is a smooth approximation of the 0-1 loss. So what AdaBoost does is reassign the weights, for example, by looking at the current set of weights for the dataset at time t and reassigning weights to them for the dataset at t plus 1. We're going to do that by examining how the particular classifier at iteration t gets or doesn't get a particular example right. Let's take the case of where the classifier gets something correct. Then y times the output will be a positive value. When we have a positive value and we times it by the alpha weighting parameter, this value will be negative, and we're going to see that the importance of this particular training example J will shrink. On the other hand, let's say they mismatch. So for example, Yj is positive, but the classifier calls it negative, or vice versa. Then this product is negative. And when we multiply it against the weighting coefficient, because we have a negative value in front, this exponential will be large, and the weight for this training example J will increase for the next iteration. So we've written it out for you on this slide, where we see that the alpha t inclusion factors in the strength of the overall classifier over all of the examples. We didn't mention anything about z of t, just a normalization which aggregates all of the weights of all of the training examples to sum to unity, so that we have a probability distribution over all of the individual instances in our training data set. So each time we go through an iteration, we are taking the weights that sum to 1 from the current iteration and reassigning the weights for the same data set, but reweighted so we can emphasize cases that the algorithm got wrong and lower the weight for instances that the algorithm got correct. This allows us to work with a very weak learner, for example a decision stump, which is the same thing as a decision tree, but just with one node. For example, we can work with a classifier that is a positive and negative ray classifier for continuous valued features. A positive and negative ray classifier basically has a direction S, either forward or backward on the ray, a particular feature that we're selecting, the ith feature out of all n features that we could select, and a particular weight or threshold theta, which tells us where we're going to start our line on. So for example, if we choose xi as our feature to split on, we can choose a particular weight theta and then a particular direction, for example in the positive instance, as a parameter. A decision stump can be visualized as an axis perpendicular plane in the real space of the input, and it's actually very efficient to optimize because we just need to go through all of the n features and decide where to place the threshold by using a divide and conquer algorithm to find the optimal point to place the threshold theta in log m time. This allows for the efficient minimization of the training cost, but on its own, a decision stump is too weak to work by itself, so typically this is arrayed in boosting. The pairing of a decision stump with AdaBoost is very common, and let's illustrate it by looking at this example on the xy plane, where the x1 would be x and the y value would be x2. We have here a dataset that's not linearly separable. What would the AdaBoost stump algorithm do? Given this original dataset, it would have to draw a decision stump. Perhaps it decides that the first dimension, x1, is good to split on, and we can get all of the negative examples right by putting the decision hyperplane here. Of course, that gets certain examples wrong. For example, the 3 positive examples here in the blue are incorrect. So after going through the first iteration, these examples are upweighted, as we can see by their enlarged size, and the rest are downweighted. With the resampled data set from the first time point, we rerun the decision stump and we get a different decision boundary. This time the idea is to get all of the positive instances correct and forsake 4 of the negative instances as wrong. This doesn't work very well either, and so we will shrink some of the points that we get correct and enlarge all of the rest of them that we got wrong. The decision stump algorithm, when run again with those reweighted examples, chooses x2 for the first time and decides to cut horizontally across here. Everything above this line would be categorized as negative, and those below the line would be classified as positive. The pink and the blue regions illustrate how the AdaBoost algorithm would weight all of the free individual stumps to combine and get an overall classifier as illustrated by the black line. Here we can see that all three of the classifiers still have gotten the circle on the middle right wrong. When we continue for a number of iterations, we can see that the decision surface continues to change, eventually getting all of the examples correct. Moving on, we can see another example of AdaBoost with decision stumps working on a much larger data set with many more iterations. It will define a piecewise linear perpendicular line segments to the input space boundary.